Let's talk a bit about uncertainty and propagation of errors. Let's say we take a measurement, say of speed, and we measure something like 15.6 meters per second, plus or minus 0.2453 meters per second. So any measurement we have should always have some uncertainty, so we have an uncertainty given here. But there's something wrong here in that our uncertainty has way more significant digits than our measurement itself. So as a general rule, we should always round our uncertainty to one significant digit itself. So 15.6 plus or minus 0.2 meters per second makes a lot more sense when we're reporting an uncertainty with a measurement. Let's consider now measurement of 423.1 meters per second plus or minus 10 meters per second. So this is a little funny too, in that our measurement has more precision in it than our uncertainty itself. And so in general, we should round our measurement to the same order of magnitude as our uncertainty. So for example, 420 meters per second plus or minus 10 meters per second would be the right way to report this answer. Let's talk a little bit about terminology. When we have a measurement, say 15.6 plus or minus 0.2 meters per second, we talk about the absolute uncertainty, delta V1, for that measurement. That's the 0.2 meters per second. We could also talk about the relative uncertainty in this measurement, which would be the absolute uncertainty, delta V1, over the measurement itself, V1. In this particular case, that's 1.3%. Or if you actually calculated it, it would be 0.013. And that helps us understand the amount of precision in a particular number itself. So now that we've talked about uncertainties, how do we add or subtract numbers which have uncertainties associated with them? So let's consider these two momenta, P1 and P2. And now I want to add these momenta to find, say, the total momentum. Well, what I would want to do for P total, I'd add P1 and P2, so I just take the measured values and add those. To find the uncertainty in the total momentum, delta P tot, what I do is I add the absolute uncertainties in what's called quadrature. So I add delta P1 squared plus delta P2 squared and take the square root of that. So in this particular case, I get total momenta of P tot 4.80 plus or minus 0.09 kilograms meters per second. Notice the 0.09 looks like it's the same as just adding delta P1 and P2. And sometimes that'll be true, sometimes it's going to be close, but more generally we should add the uncertainties in quadrature rather than just adding the uncertainties together. This works the same way if I want to subtract these two numbers, although there's an important thing that happens when you subtract. So let's say I have the quantity Q, which is P1 minus P2. The uncertainty in Q is still delta P1 squared plus delta P2 squared, square rooted. So I still add the absolute uncertainties in quadrature. So my total value Q is 0.08 plus or minus 0.09 kilograms meters per second. But notice now that the relative uncertainty, delta Q over Q, is in fact 110% now. So the absolute uncertainty is the same as when I added, but the measured value is actually much smaller in this case. And so when you subtract numbers with uncertainties, you can end up with really large relative uncertainties, particularly if the numbers are really close to each other. So keep that in mind. What about if you multiply or divide two numbers? So say I have a measurement of a mass and a velocity, each of which have uncertainties associated with them, and I want to calculate the momentum. In this case, the rule is you add the relative uncertainties in quadrature. So delta m over m squared plus delta v over v squared, all square rooted. So in this particular case, I would come up with delta p over p is 0.018, so a relative uncertainty of 1.8%. When I calculate the measured value of the momentum p, and then I can multiply through, I can report my answer as 67 plus or minus 1 kilogram meters per second, where the 1 is what happens when I multiplied 0.018 times the measured value of p. What if you have a more general function, though? This is called propagation of errors, figuring out how to calculate the uncertainty in more general calculations of quantities with uncertainties. So let's say I have a 20 kilogram object, with some velocity, which has uncertainty associated with it. What is the kinetic energy? Well, I know I can calculate the measured value of the kinetic energy, 1/2 mv squared, and using the central measured value here, okay, I can calculate k. But what is the uncertainty in the kinetic energy? Or more generally, what is the uncertainty in some general function, say, of the velocity? To do this, we need to take a math aside. So let's say I have a measured quantity, x, and some function of that measured quantity, f of x. So in this case, that'd be, say, x would be the velocity, and f of x would be the kinetic energy, which is a function of the velocity in our example above. Well, our measured quantity has some uncertainty, delta x, and that will lead to some uncertainty in the calculated quantity, f of x. So it'll lead to a delta f. So how do I figure out what the delta f is? Well, it just has to do with the slope. And so in order to figure out how much uncertainty I have in delta f due to a little bit of uncertainty in delta x, I can see it's just the slope, df dx, times the uncertainty in x. That tells me what the uncertainty in the function is. And we call this general expression propagation of errors, where you're taking derivatives of the function. Okay, so in our example, we can calculate the kinetic energy to be 294 joules. The uncertainty in the kinetic energy is then dk dv times the uncertainty in v, which is just mv times the uncertainty in v. And so that comes out to be 1 joule. So I'd report the total kinetic energy in this case as 294 plus or minus 1 joule. So that's how I would calculate the uncertainty, delta k, in the kinetic energy, or more generally in a function. What if you have multiple variables? Well, then we're going to do propagation of errors again, but for multiple variables. So let's say we still want to calculate kinetic energy, but now the mass and the velocity both have uncertainty associated with them. So my kinetic energy is now a function of two variables with uncertainty, m and v. Well, in function with two variables, I would do essentially the same thing. I now have x plus delta x, y plus delta y. And so the uncertainty in f, in my new calculated quantity, is the partial derivative of f with respect to x times delta x, all squared, plus the partial f with respect to y times delta y squared, all square rooted. Or another way of saying that is you just add the propagation of errors for each variable in quadrature. Do what you normally would have done with one variable, and then add them all up together in quadrature. If you had 3 variables, 4 variables, each with uncertainties, you'd just keep adding them inside the square root in quadrature. So in our example, again, this looks like delta k is partial k partial m times the uncertainty in m squared, plus partial k partial v times the uncertainty in v squared. I can calculate those partial derivatives, and so then I find an uncertainty in k of 2 joules. So I'd report this result as 332 plus or minus 2 joules. So that's how I would do that in multiple variables. Let's just take a step back and use our expression for propagation of errors to derive the common formulas that we saw at the beginning of this slideshow. So in particular, addition and subtraction. So we have two quantities, x and y, both with uncertainties. What is the uncertainty in f? Well, we already learned that at the beginning of the video. You can go back and look, but let's use our propagation of errors to rederive that. So the partial derivative of f with respect to x and partial derivative of f with respect to y both happen to be 1. So when I use my expression for the uncertainty in f, delta f, I just get delta x squared plus delta y squared, all square rooted, or adding the absolute uncertainties in quadrature, which is exactly what we were told to do at the beginning of the video. How about multiplication and division? So let's say I have two quantities, x and y, both with uncertainties, and I want to calculate a new quantity, f. Well, again, I'll calculate the partial derivatives, partial f, partial x, and partial f, partial y, so that the absolute uncertainty, delta f, is given by adding the propagation of errors in quadrature. But it turns out to be much more useful to write the relative uncertainty for multiplication and division. So I'll write it as delta f over f is equal to, now substituting in the partial derivatives, square root of y delta x squared plus x delta y squared, and that's all over x times y. It looks like a mess, But if you distribute the x times y inside the square root, you'll find that things cancel really nicely, and you just get the sum of the relative uncertainties in quadrature. So delta x over x squared plus delta y over y squared, all square rooted. Which again is what we were told for multiplication. You can do the same thing for division and it turns out it'll work. How about one that we didn't see at the beginning, but it shows up a lot? So we have a new quantity, which is just multiplying the measured quantity by a constant. What do we do in this case? Well, propagation of errors tells us the answer. You take df dx and multiply that by delta x. Well, df dx in this case is just the constant c, and so the uncertainty in f is just the constant times the uncertainty in x. So whenever you're multiplying by a constant, just multiply the uncertainty by the same constant, and that gives you the new uncertainty in your new quantity. So that's with the mathematics of propagation of errors. Let's just talk for a brief second about reasoning with relative uncertainty. So consider we have a new quantity, say f, which is x times y. Both x and y have uncertainties. Well, we know now that the relative uncertainty in f is just written as the sum of the relative uncertainties in quadrature, delta x over x squared plus delta y over y squared. But consider now that one of these quantities that we've measured is more precise than the other. And in particular, let's let delta x over x have a relative uncertainty of 14%, but delta y over y have a relative uncertainty of, say, 0.2%. Well, clearly the relative uncertainty in x is going to dominate inside the square root. And so the relative uncertainty in f is going to be dominated by the relative uncertainty in x. There's going to be something like 14%. So this is a good way when you're looking at some measurements to kind of estimate the relative uncertainty in your final answer by looking at the largest relative uncertainty in whatever measurements you've taken.